Assalamu alaikum. Good morning, good afternoon, and good evening. Thank you all for joining us for this inaugural JRC Memorial Lecture arranged by the Buet Alumni Association. We appreciate your time and efforts to preserve JRC's legacy. I'm Dr. Kausar Jahan, professor and head in the Department of Civil and Environmental Engineering at Rowan University, and I'm also a Buet alumni. As we start this inaugural lecture, and before we introduce our esteemed speaker, we will hear from a number of speakers, starting with architect Qazi M. Arif, who's going to give some introduction and background. He's the Secretary for Communication and Publication for the Buet Alumni Association, and also the co-chair of the JRC Memorial Lecture Advisory Committee. Qazi M. Arif.
Ladies and gentlemen, good evening, good morning, and good afternoon. The annual JRC Memorial Lecture has been established by Buet alumni to share knowledge of today's practitioners with tomorrow's engineers, architects, planners, scientists, public policymakers, and more. This lecture series is inspired by the work and vision of Professor Jamilur Reza Chaudhuri, popularly known as JRC, National Professor of Bangladesh. It is an annually recurring lecture intended to be organized preferably in November, his birth month, to celebrate the legacy and vision of JRC. The precise date is a little flexible depending on the availability of the distinguished speaker for the particular session. The inaugural session of JRC Memorial Lecture is happening virtually tonight. The focus in general of JRC Memorial Lecture is to bring renowned global leaders, visionaries, and contributors to share and promote intellectual thoughts and knowledge for the future of the world. The target audience includes students, alumni, scientists, practitioners, policymakers, and social leaders. It is a matter of pride and pleasure to have Dr. Dan Frangopol tonight as the distinguished speaker. As we all have come to know by now, Dr. Frangopol is the Fazlur Rahman Khan Endowed Chair and Professor, Department of Civil and Environmental Engineering of Lehigh University, USA. You will be presented with more details of Dr. Frangopol's acclaimed and commended career and contribution as we proceed further into the event. Professor Jamilur Reza Chaudhuri was an internationally recognized civil engineer, educator, researcher, and administrator. He was the most eminent personality in the engineering community of Bangladesh that made a great impact on science and technical education, the engineering profession, and national development, particularly the development of infrastructure and IT sectors of the country. Professor Chaudhuri served as the Vice Chancellor for BRAC University and the University of Asia Pacific in Bangladesh. He was awarded the prestigious Ekushe Padok in the category of Science and Technology in 2017 and the most honored National Professor Academic rank in 2018, both by the government of Bangladesh. The mission of Buet Alumni Association is to create a purposeful and forward-looking organization for the alumni of Buet for their social, cultural, and professional quests and interests. Professor Chaudhuri was the president of Buet Alumni Association from 2005 until he breathed his last in 2020. He was instrumental in bringing together the alumni of Buet from all over the globe in the pursuit of realizing the association's mission and vision. The Board of Trustees, the Executive Committee, all members of Buet alumni, and the members of the Advisory Committee for JRC Memorial Lecture are happy to pay the well-deserved tribute to its perpetual president and National Professor Jamilur Reza Chaudhuri through this lecture tonight. I'm sure this will benefit thousands of people around the globe and shall touch their heart and mind with the passion and spirit of this brightest beacon of light of our time. Thank you, ladies and gentlemen, for lending me such a patient hearing.
We appreciate your remembrance of JRC, and those of you who are joining in late, this is the live inaugural JRC Memorial Lecture Session. And I'm Dr. Kaustubh Jahan from Rowan University, professor and head of civil and environmental engineering. We are currently listening from speakers who are providing some background information about the lecture. Next, we are going to hear from Engineer Muniruddin Ahmed, Acting President of the BUET Alumni Association, and he will be presenting his address of welcome.
It is a great pleasure for all of us that BUET Alumni Association has taken a resolution to arrange Jamil Reza Chaudhuri Memorial Lecture annually in the month of November, his birth month, to share knowledge of today's practitioners with tomorrow's scientists, engineers, public policy makers, and many more. The main focus of the memorial lecture is to bring renowned to global leaders, visionaries, and contributors to discuss, share, and promote intellectual thoughts and knowledge for future world. We have been inspired by the work of Jamil Reza Chaudhuri, the National Professor of Bangladesh, former President of the Institution of Engineers Bangladesh, founder President of the Alumni Association of Bangladesh. JRC was an internationally recognized civil engineer, educator, researcher, administrator, and whatnot. He happened to be the most eminent personality in the engineering community of Bangladesh that made great impact in science and technical education. He has made tremendous contribution to many national infrastructure development such as Jamuna Bangabandhu Multipurpose Bridge, Podda Bridge, Kornofuli Tunnel, Metro Rail, Elevated Expressway, etc. Moreover, JSC served BUET as a professor of civil engineering for almost 30 long years. He has also the Vice Chancellor of Bragg University and University of Asia and Pacific. In 2017, he was awarded the country's most prestigious Ekushe Padak by the government of Bangladesh for his remarkable contribution in various fields, especially in the category of science and technology. Now I wish to welcome all the first JRC Memorial Lecture in 2021 titled Risk, Management and Sustainability of the Civil Infrastructure under Lifetime Hazard including Climate Change. Finally, I wish to express my heartfelt thanks and gratefulness to the speakers, organizers, and as well as the participants.
Our next speaker is no other than the Vice Chancellor of the Bangladesh University of Engineering and Technology and the Chief Patron of the BUET Alumni Association, Professor Satya Prasad Majumdar. Ladies and gentlemen, the Vice Chancellor of BUET.
Dr. Jamil Reza Chaudhuri is the brightest star in BUET sky. He was one of the best students of BUET, one of the best teachers BUET could ever had, and undoubtedly the most reputed engineer BUET has ever produced. This is my honor as the present Vice Chancellor of BUET to commemorate Dr. Jamil Reza Chaudhuri. Dr. Jamil Reza Chaudhuri earned his Bachelor of Science in Engineering degree in Civil Engineering from BUET in 1963. He earned first class and secured the first position in his class. Upon graduation from BUET, he joined the Department of Civil Engineering as a lecturer and began his long teaching career. In September 1964, he was awarded a scholarship to pursue Master of Science in Engineering in Structural Engineering in the United Kingdom. Later in 1968, he was conferred a PhD degree on the topic of shear wall and structural analysis of high-rise building. After completing the PhD, he returned to BUET in 1968 and joined as the assistant professor. He was promoted to associate professor in 1973 and as a professor of civil engineering in 1976. Until 2001, he was working as a professor of civil engineering at BUET. Dr. Jamilur Reza Chaudhuri served as the head of the Department of Civil Engineering and also as the Dean of the Faculty of Civil Engineering at BUET. He was also entrusted with developing a computer center at BUET and was appointed as the director of the center for about 10 years. Throughout his long career at BUET, he has played vital roles in academic developments. Also, after he left BUET in 2001, he was always in touch and served as one of the syndicate members for 4 years. Currently, BUET alumni are united around the world by a strong brotherly relationship. Dr. Jamilur Reza Chaudhuri played a key inspirational role behind this brotherly relationship. Through BUET Alumni Association, Dr. Jamilur Reza Chaudhuri was involved in many noteworthy activities within BUET and around the country, even to the moment when he breathed his last. Dr. Jamilur Reza Chaudhuri made unparalleled contributions toward the socio-economic development of Bangladesh. Almost all noteworthy infrastructural development in the country received his excellent expert service. He played leading technical and advisory roles in the conceptualization and construction of Bangabandhu Bridge, Padma Multipurpose Bridge, Karnapuli Tunnel, Dhaka Elevated Expressway, Dhaka Ashulia Elevated Expressway, and many more. He has proved that Bangladeshi engineers can lead the challenging mega projects and complete them successfully with confidence. Bangladesh will remember his contributions to infrastructural projects for decades to come. His contributions to the infrastructural development of Bangladesh surely will have improved lives of millions of people of Bangladesh. He will remain as an integral part of the story of Bangladesh's success in decades to come. Dr. Jamilur Reza Chaudhuri was like a source of light as a lighthouse for us. His works and memories will forever remain our inspirations. He helped us rise nationally and also globally. His glows helped us shine brighter both within and outside the country. We cannot express our gratitude enough to keep his memories alive forever in BUET and pass his dedications to the generations to come. We have renamed the building of the civil engineering to Professor Jamilur Reza Chaudhuri Civil Engineering Building. Let us learn from the life of Dr. Jamilur Reza Chaudhuri and pray for his eternal peace.
Thank you, Dr. Mojumdar. We appreciate that you were able to take time from your very busy schedule and record this warm message to not only honor the legacy that JRC left behind, but also to address BUET alumni and other visitors who are listening to this live session. The moment that we have all been waiting for, the introduction of our esteemed speaker today. It is with extreme joy and humility that I introduce our inaugural speaker for the JRC 2021 Memorial Lecture, Dr. Dan M. Frangopal. Dan currently is the Fazlur Rahman Khan Endowed Chair and Professor of Civil and Environmental Engineering at Lehigh University, which is located in Pennsylvania. It is no coincidence that Dr. Frangopal has been selected to initiate and start this lecture series. His passion and interests actually align very well with the passion and interests of JRC. Infrastructure, engineering education, and extreme storm events, natural disasters, climate change were terms that were close and dear to the heart of JRC and are very close and dear to the heart of our speaker today. Dr. Dan M. Frangopal has an extremely distinguished career, and 2 or 3 minutes will not do justice to all his accomplishments that he has had. He's recognized as the leader in the field of life cycle engineering of civil and marine structures under various types of hazards. He's the founding president of the International Association of Bridge Maintenance and Safety and International Association for Life Cycle Civil Engineering. He has authored, co-authored books, more than 60 book chapters, 430 articles and archival journals, including 11 prize-winning papers. He's the recipient of numerous prestigious awards and medals and prizes from ASCE, IABSE, SAE, and other professional organizations. He has served in the capacity as a consultant and advisor to companies in North America, Asia, and Europe. Dr. Frangopol holds 4 honorary degrees, doctorates, and 14 honorary professorships from global universities. It is with extreme joy and pleasure that I introduce Dr. Dan Frangopol as the inaugural lecturer for the annual GRC Memorial Lecture Series, which we are kicking off to celebrate not only GRC's legacy, but also his birth month, which was in November. The title of Dr. Frangopol's presentation is Risk, Resilience, and Sustainability of Civil Infrastructure Under Lifetime Hazards, Including Climate Change. Ladies and gentlemen, thank you so much for joining us from all around the world today as we listen to this very important presentation that tells us about the future of civil infrastructure under extreme lifetime hazardous situations. So it is with joy and pleasure that I introduce and allow Dr. Frangopol to make his presentation. And thank you, Dan, from the Bouet Alumni Association and all the alumni and members who have joined us from our professional societies today. Thank you.
Ladies and gentlemen, good morning, good afternoon, good evening. I want to thank all members of the Bouet Alumni Association and all the advisors of the GRC Memorial Lecture who selected me as a speaker, inaugural speaker for the GRC Memorial Lecture. It is indeed a very high honor for me. My talk will be in general terms. I will not enter in computational details, and I want to try to convey the state of the art in the field of risk, resilience, sustainability of infrastructure systems under hazards, including climate change. I know that your country, Bangladesh, has earthquakes, a lot of wind, and also a lot of things that are detrimental to the civil infrastructure systems. I have to thank my former and current students and postdocs for their contributions. Without them, I'll not be here today. I have also to thank many funding agencies from United States and other countries, but especially for the National Science Foundation, Federal Higher Administration, Office of Naval Research, NASA, ArcelorMittal, and other agencies. I want to mention the accomplishment of GRC. This accomplishment was mentioned also before the speakers, but it's very important to mention that he was the head of civil engineering, established the Bouet Computer Center, first vice chancellor of Black University, vice chancellor of University of Asia Pacific, president of Bangladesh Mathematical Olympiad, president of Bouet Alumni Association. He envisioned that all Bangladeshi children having access to the internet, education, health services, clean water and sanitation, and the climate resilient future. He built bridges with students, relatives, friends, and peers. And I like very much his favorite quote: if you do not have integrity, you have nothing. We discussed about this yesterday when I met Professor Joan, and we talked about his legacy and his family. I was also lucky to be the inaugural Fazlur Rahman Khan chair at Lehigh University. And I organized a distinguished lecture series dedicated to Fazlur Rahman Khan, who know very well GRC, and I want just to introduce this lecture series. This lecture series began in 2007 and is continuing. We have until now 48 distinguished speakers. This series was created by the friendship between Professor Lynn Biddle and Dr. Fazlur Rahman Khan. Professor Biddle was a very distinguished professor at Lehigh University. And following the death of Fazlur Khan in 1982, Bill organized the establishment of Lehigh University of the Fazlur Rahman Khan Endowed Chair. You know all that Fazlur Khan is the father of tall buildings, and in many ways, the father also of structural engineering, modern structural engineering. He was a pragmatic visionary. He joined SOM, which is a very important engineering firm that is still today in Chicago, in San Francisco, London. And he was building and designing tall buildings, including the 110-story Sears Tower, which was the tallest building in the United States since its completion in '74. It was also the tallest building in the world for about 20 years. His characteristic statement to an editor in '71, having just been selected Construction Man of the Year by Engineering News Record, is commemorated on a plaque in the center Chicago, saying that the technical man must not be lost in his own technology. He must be able to appreciate life, and life is art, drama, music, and most importantly, people. He died at 53 years old, very young, but he left us a lot of things that we can learn even today in designing tall buildings and other structures. These are the speakers, and we begin in 2007. Generally, we have 3 speakers per year. These speakers are from United States, from Asia, and also from Europe. We have a website with all the speakers. I just say that these were the speakers from 2011, 2015, from 2016, 2020, and this year we have virtual speakers. These are a mixture of architects and civil engineers. These were the speakers in spring, and these are the 2 speakers in fall. As I mentioned, infrastructure is a very important topic, and as you know, in the United States, we are lucky now to have a bill of infrastructure that is 1.2 trillion, looking at evaluation of rehabilitation of many structures, including bridges, including tunnels, including transit systems, drinking water, piers, school facilities, and so on. We have to look at infrastructure in different ways. We can begin to look at the components of a structure, of a system by itself, a structure by itself. We can look at interaction between different type of components in a structure, and also we have to look at network of structures, and also a network of networks, and even the interaction between different types of infrastructure. The American Society of Civil Engineers, which is the largest association of civil engineers in the world, has about 150,000 members. Every 4 years has a report card, and this report card gives the status of our infrastructure. The last 2 reports, one in 2017 and the most recent this year, grade different type of infrastructure, and in general, the infrastructure got a D+ in 2017 and a little bit better, a C-, but not a big grade, of course. And the bridges, you can see, were C+ and now downgraded to C. I was lucky to be a member of Industry Liaison Council, which is a Leaders Council. This is a council that is providing advice to the board of directors of American Society of Civil Engineers. And the ACE Grand Challenge is now to significantly include and enhance the performance and value of infrastructure projects over their life cycles. to reduce the lifecycle cost of infrastructure by 50% by 2025, and fostering the optimization of infrastructure investment for society. So it's very important to see these new concepts, the concept of life cycle, the concept of optimizations that are applied now in dealing with our infrastructure. So optimization of life cycle should also be incorporated with the hazard management. The resilience is an important quality of infrastructure, was defined 40 years ago in the context of sustainability as the ability of communities and ecosystem to withstand external shocks or perturbation to the infrastructure and to recover from such events. We have natural and man-made hazards like earthquake, hurricane and floods, and fires. I know we have this also in Bangladesh. Population growth is also an important topic. And since 1970, the world population has grown by more than 110%. So there are about 3.8 billion people in 1970. Now there are about 8 billion. So the rapid urbanization will increase exposure to natural hazards. 10 years ago, the United Nations Office for Disaster Reduction reported the natural disaster resulted in about 370 billion of direct losses. These are only direct losses. On top of this, we have many indirect losses. So now we have a lot of losses due to different events, including climate change. Hazard risk and resilience assessment are of great importance in a life cycle context. So infrastructure systems are critical for the economy and the society. You have hazard and climate change, aging and deterioration processes, population growth and urbanization. And the new performance indicators are now risk, sustainability, and resilience. We used to talk about safety a lot. And this, of course, is an important and very important reliability, safety, very important parameter, but also risk and sustainability and resilience are now doing the most important things that we can evaluate systems. About 25 years ago, I drew this figure with some of my students in which you have the performance of a system and time. So time is an important parameter, and from here the concept of life cycle evolves, in which you have an indicator that is almost constant at the beginning, and after you have deterioration processes, for example, corrosion, fatigue, that will find that the performance is going down, and at a point you reach a target level. So the service life is between this point and this point. If you want to extend the life, you can do different repair or maintenance activities, but anytime you do such activities, you have to pay for. So cost is an important parameter. You can see that you can extend the life from this point to this point by doing this repair or doing essential maintenance. You have to pay much more and you can extend the life even more. The problem is that all these indicators and all these times basically are variables. You don't know exactly what is the performance of the structure at the beginning. You don't know exactly when the deterioration will occur. You don't know exactly what is the deterioration rate. And also you don't know if you repair a system, how much exactly the performance is improved. So for this reason, the life by itself is a variable, could be shorter or longer depending on the combination of these uncertainties. As time evolves, you can see that the life cycle is also more spread out. So it's difficult to predict the life if the time is increasing by. We apply this concept to bridges and naval ships. Of course, you can apply to any other type of infrastructure. Generally, this performance indicator is decaying with time, and you have a smooth deterioration process due to things like corrosion, fatigue. But when you have earthquake, flood, collision, or other natural hazard, this deterioration is going down. The problem is that how much you lose, how much is the deterioration going down? Is it above or below a target level? So we have to look at these aspects. As I mentioned, you have uncertainties, you have performance indicators, you have reliability and redundancies, those indicators that are now very much accepted. But in addition to this, you have consequences. So how we can relate these consequences to our performance indicator. So the risk is an important indicator that combines the reliability, probability, and so on with consequences of failure. So you can see here that you have two, here is a graph which is the probability of failure of a system and the risk of the system. And you can have two systems that are the same, but from the viewpoint of safety, you can see that probability of failure of system A is dominating in this at the beginning. But here, from the viewpoint of risk, is system B that is dominating. So it means that two systems that are with the safety that could be comparable, the consequence of failure could be very different. If you have a breach in a very high populated area that is failing, or the same breach with the same safety in an area that is not populated, of course, the safety could be the same, but the risk is different. So we have to look at the risk as a very important indicator, which include consequences of failure. As I mentioned, maintenance is an important parameter, and now we are looking a lot of maintenance. Sometimes countries, very developed countries, invest more in maintenance than in constructing new buildings or bridges or infrastructure systems. And the problem is how to apply this maintenance in order to increase the life. How to look at maintenance that can be at a level that is a target level. Here you have rehabilitation, so these are costly maintenance activities, but you extend the life. Or you can have preventive maintenance in which you don't improve the performance, but you delay the deterioration. For example, painting a steel bridge. You prevent corrosion, you don't improve it, but you prevent the spread of corrosion. Many researchers look at mechanical models, a finite element analysis, a structural health monitoring is a very important field. And you have to do updating in order to have a better estimation. So Bayesian updating also a very important things that we have to look in order to have a better estimation of the life. As I mentioned, cost can be larger during the life of the system. So in general, projects were given by the initial design and construction cost, but sometime during time you have repair, you have rehabilitation, you have maintenance activities, and the cost is accumulating. So the final cost, the total lifecycle cost, could be much larger than the initial cost. So these two parameters, cost and performance, are parameters that have to be taken into consideration. You try to minimize the cost and you try to maximize the performance. This is just an optimization problem in which you try to minimize the lifetime total maintenance cost subjected to different constraints, reliability constraints, redundancy constraints, risk constraints, and you have to provide a solution that is optimal. With my students and postdoc, we built a computational platform which has different modules like reliability, risk sustainability, maintenance, inspection, optimization, and finally, a decision-making process in which you look at different type of systems and you want to optimize them. Sustainability is an important concept, as I mentioned. It involves not only the economic part, as I mentioned about cost, but also environmental aspect and social aspect. So sustainability, a very, very important concept, and to try to do and to design sustainable structures. Just to give you here an idea of a network of bridges in Los Angeles area, about 20 bridges. We look at this system about 2-3 years ago, and this is a higher transportation network in Los Angeles County, and we look at these bridges individually and being part of a network. So we raise them individually, but also being part of a network. We can see these are the 20 bridges here, and these are the network rating, and this is a project rating, individual rating. So being part of a system means that you have to not neglect the fact that the bridge is part of a system. If a bridge will fail by itself, it's important if the bridge is a very important part of the network or in a part that is not so important. So not only to look at the structure by itself, but to look at the structure participating in a network of systems. As I mentioned, we look at all these aspects, including modeling of deterioration, the hazard and structural response, the life cycle assessment of infrastructure, and the multi-attribute utility theory. This is a very important theory of utility that give you sustainable metrics. Always you have to maximize the utility. And we can provide a sustainable and resilient informed lifecycle management decision process. This is a computation platform that I mentioned. I began to work with it with my students in Colorado when I was at University of Colorado in Boulder about 30 years ago, and we develop now some modules that are related to sustainability, to lifecycle optimization, and finally, we can make optimal lifecycle management, and we apply this to bridges and naval ships. Concept of lifetime resilience, we don't have time to talk too much about this, but I want just to mention some developments. If you have a system and the system will perform satisfactorily at a certain time, and after you have a natural disaster like an earthquake or a flooding, the functionality of the system is going down. And after you have a period in which you have to decide about what to do and how to repair the system to arrive at the same type of functionality that was at the beginning. You can arrive also at a level of functionality that is lower. Of course, how to define these resilience parameters is an important factor. And we define with one of my previous students, Alberto Deco. He is now working for Boeing in California, and Dr. Bocchini, who is my postdoc, and now he's an associate professor, my colleague at Lehigh University, quantified by this highlighted area divided by the total area. So we have the initial functionality, the time of hazard occurrence, the residual functionality, the idle time, the recovery path, and the functionality after recovery. This plot is also from a paper with Dr. Bocchini that was published 7 years ago, in which you look at the difference between resilience and sustainability. A resilient structure, of course, has to be a structure that will take into account hazards that could happen during the lifetime, and they could recover. But this happen only at a certain point in time. A sustainable structure is a structure that has to be sustainable all this life. And is a big difference between resilience and sustainability that is perhaps not well understood. A sustainable structure has to be resilient. but a resilient structure is not necessarily sustainable. So you can have a structure that is resilient but is not sustainable, but you don't have a sustainable structure. It has to be always a resilient structure. In addition, we introduce the concept of lifetime resilience. Sometimes you look at resilience at a given point in time, but you can see that the resilience has to be for the lifetime. So if you have, for example, this is a normal deterioration process, and these are some events that occur, extreme events, extreme event 1, extreme event 2, extreme event 3. And you do repair here until the deterioration, what will be the normal deterioration process. So these are repairs that are doing, and you have the resilience associated with minimal repairs is time dependent. This one, of course, is a replacement, removal, demolition, and rebuilding, which you have to do the performance until the initial performance level. And these are things that I wanted to mention. The so-called MAUT is a multi-attribute utility theory that is used for sustainable systems. You have the economy, society, environment. You have to deal with all of them. And you can see the same figures that I mentioned previously, but also the impact, the economic, social, and environmental impact on cost and how to deal with all these things. And we did several applications on bridge infrastructures. This utility, I mentioned utility is a very important parameter, and this utility has to be always maximized. The best scenario will be when utility is equal to 1. The worst scenario is utility is equal to 0. But in all this process, you have to look at the economic utility, the social utility, the environmental utility, and you have to deal with decision maker. Some are risk averse, some are risk taking, some are risk neutral. And there are different formulation type of utility function. I will not enter in detail, the exponential, quadratic, logarithmic formulation, and combine different attributes using this concept of multi-attribute utility and to seek the optimal decision by maximizing utility values. In addition, you can also weight different factors. You can weight the economic impact, you can weight the social impact, you can weight the environmental impact. So for a structure, you can say economical impact, I want to be 60%, social impact 20%, and environmental impact 20%. Or if the environmental impact is the most important, you can weight this very heavily, and the economic impact not so heavily. So for the application to infrastructures, you look at the social impact, including the fatalities, the total travel time, for example, if it is a network of bridges, the total travel distance. For the environmental impact, you have CO2 emissions, energy consumption, and so on. And I know that Bangladesh was hit by several earthquakes, so I saw that I'll present a small application here in several slides that we did with a network of bridges in California. So if you look at the bridge system, you can have a bridge that is not damaged, slightly damaged, moderate damage, major damage, complete damage. These are exclusively events, they're mutually exclusive and collectively exhaustive events. And you can look at all the consequences and the probability that you have an earthquake of a given magnitude, you have a damaged state, and you have to make summation of all these conditions. So looking at this definition, we look at the probability of the hazard occurrence. The probability that if it's a hazard occurrence, you'll have a damaged state. And if I have a damaged state, what will be the consequences? And you sum over all the damaged state and over all the consequences, and you have this metric for sustainability. As I mentioned, you have the social aspect, fatalities, injury, time waste, downtime, the economic aspects, including different type of cost, and the environmental aspects. To apply this to this network of different bridges, these are single-span, simple supported concrete, multi-span, continuous concrete, multi-span, single supported concrete bridges. This was a network in California, and will have 16 bridges and 4 nodes. You can see USGS provided the data for the Santa Andrea fault and the other faults here, and the network is placed here, not far from the Santa Andreas fault. We look not only at the bridges by themselves, but also at the links, because if a link between 2 bridges is damaged, of course, you cannot travel from one bridge to another one. So you have a seismic performance of the link, which depends on the damage state of the bridges in the links. And this is a computational approach in which you look at the each link, all the links, and you look at all the bridges, and you compute the social metrics, you compute the environmental metrics, and you compute the economic metrics, and finally you compute the total risk and use this information in decision making. This is a result that we obtain here for this network, in which you look at all the costs. These are the expected life cycle loss in millions of dollars, looking at the fatality loss, the expected operational loss, expected total loss, which is all the sum. And in addition to having not only the total loss and variation with time, we look at the dispersion of this loss. So this curve that is here, which is expected loss, you look at the dispersion, and you can see that the dispersion is increasing with time. Now, another parameter that is very important is the time horizon. I will analyze this network for 40 years, or I will analyze this network for 5 years, or for 70 years, and so on. So we analyze this network in 2 situations, with a time horizon of 40 years, this is it here, or with a time horizon of 70 years, which is this. Of course, the loss in US dollars will be different, and the spread will be also different. You can see here's the median value for the 75-year loss is about 13, and here is about 4. Of course, you multiply by these factors. With now the student, we introduce this renewal reward processes, which is quite a very good process for looking at the history of deterioration and history of occurrence of different hazards. You can see here you have the capacity that is diminishing time, and sometimes you have events like floods, sometimes you have another event like earthquakes, and these events, you can see that they are not up to this curve, but you can have failures if the capacity is less than the demand. So these are the failures that occur, these are other events. And you can look at the failure occurrence process, which is a renewal process, and consequences. You can see if you have failures here, you have these consequences, and this is a so-called life cycle consequence, which is a renewal reward process. And in addition, we also introduce the variability of these processes, and all this thing was published with application in the Journal of Reliability Engineering and System Safety. Climate change, an important factor. I'll just give an overview. These are some data of the global temperature anomalies compared to the period of 30 years. From the baseline was 51 to 80 years, but after we can look at all this period of time, and you can see the temperature anomaly here, which is basically 1 degree Celsius increase in this time interval. This is another climate change graph looking at tropical cyclones. I know you have this in Bangladesh too. And these are for different parts of the world, North Indian, South Indian, and so on, North Atlantic, South Pacific, in which you have all categories here. And I look at the precipitation rate. This is a force factor. This is a precipitation rate, increasing very much everywhere. Also, lifetime maximum intensity, which is this factor 3, is also increasing, but not so much like the precipitation rate. These are some graphs from the United States, You can see here the global sea level rise between 1880 and 2020, and the percent of land area, also some wildfires and drought in Southeast United States, the wet part and the dry part. In addition, as I mentioned, the sea level rise is an important factor, and the damage can be further compounded by the sea level rise. And you can see all this part of the Atlantic with a very high sea level rises until almost 8 inches, and the other part of the US not so much affected. Flooding is a very, very big problem. And this graph show you two important parameters. What is the average number of floods day per year? You can see in the 50 were almost 5. In the 2010 now about 30. And this is for each town. So you compare this yellow line with the blue, and you can see all this very, very high raise in the average number of floods per day. Also, for 3 different cities, Boston, Philadelphia, and Washington, we look at the average number of floods events per year. In the 50, you have, for example, for Washington, almost 5. Now, only is a 5-year period between 2010 2015, this number was increased to about 33. The same thing for Philadelphia and Boston, but especially for Washington, D.C. is important. Also, these hazards are interacting. If you have a bridge, this is from a paper published with Professor Akiyama, who is from Waseda University and visited me twice during his sabbatical. This climate change impact of civil infrastructure, you see a bridge here that is affected by corrosion, and then elevated temperature exacerbate corrosion. But you have storms, you can have deck unseating by hurricanes. It's a problem that we study in the east part of the United States. You have the wind, and you have scour. All these are events that have to be considered during the lifetime of a system that is deteriorating in time. And the physics-based climate projections are for 2 types. The representative concentration pathways, the so-called RCP, and the global climate model, GCM. You see here this global climate model in which you have the horizontal grid is latitude and longitude, and the vertical grid is the height of pressure. And here are the RCPs for different values between 1950 to 2000. You can see quite a not so much spread, but after in predicting what happens in the future, of course, there are very different predictions. I think that also is important is the fact that with the hurricanes now and with the climate change, you have also the surge level that is different. You see Camille hurricane was a category 5, this category 5 in 69. The speed was very high, about 200 miles per hour, and the 22-foot surge. But in Katrina, which was 2005, which is only category 3, with less wind, the surge was 28. So you can see that during time, because of the increase in raise and also in temperature, this surge is becoming larger. So if you look at a specific region, for example, during Katrina, this region is Miami-Dade in Florida. You have all the records, and you can see from 1900 to 2000, and also the frequencies, the wind speed. And we can, from this chart, which is a historical one. You can look at all the categories of hurricanes from tropical storm to hurricane number 5 and produce this future projections. So we approach this with two climate adaptation. One is a top-down approach, and what are the future scenarios, and the other one is a bottom-up, which is scenario-neutral approach. What will trigger an acceptable risk? All these are documented in some recent papers. And we look at the region of Lehigh. You can see this is Pennsylvania, and Lehigh Valley is the northeast of Pennsylvania. We apply this concentration pathway, representative concentration pathway, this 3-1, and you apply 18 global climate models. We look at the timing we see between 2020 and 2100, so 8 years, in which you produce with these climate futures and global climate models, these charts for different RCP, including the annual mean daily maximum temperature, the annual mean daily minimum temperature, and the annual precipitation. And we having the access to the soil and water assessment tool produced by USGS, United States Geological Survey. We look at the land use, the hydrologic soil flow group, and the slope. And you can see here for the upstream and from downstream. And here we look at the scour process. In addition, we look at the failure of deck by unseating, and also due to damaging corrosion in the hurricanes. And we look at the optimal management strategy for coastal bridges vulnerable to corrosion and hurricane damage. And this can be drastically improved from high-risk, low-cost solution to low-risk solutions through minimal investments. Here is a so-called Pareto set, in which you have two objectives that you want to combine. One is to minimize the life cycle cost, and one to minimize the maximum life cycle risk. So you can choose solution. For example, if you want to minimize the maximum risk, will be this, but will be expensive in terms of cost. Or if you choose a solution in which you don't have too much to pay, but the risk is going up. So you have to look at how to compromise these things. So this is a general chart for civil infrastructure for climate adaptation, in which you look at different aspects like climatology aspect, hydrology, meteorology, structural engineering, geoinformatics, transportation engineering, optimization decision theory. And basically the structural engineers, they have a role in this, but a small role. They have to interact with many other people and many other specialties. An important problem is also the problem of interdependent infrastructure systems. You look at system of systems. These are dynamic systems that evolve with time. You have water, power, communication, transportation, and so on. And of course, you have to look at the system level functionality and the community resilience. You have a Center for Community Resilience in the United States, and they are looking into this. This is Colorado State University. So all what I mentioned in this talk is also summarized in two recent books. One is Life Cycle of Structure and Uncertainty. My co-author is one of my students who graduated at Lehigh 10 years ago. And this one that will is now in press will be available in February, about safety, maintenance, and management in a life cycle context. Dr. Jahan mentioned about two associations. One is this International Association for Bridge Maintenance and Safety. This was created in 1999. We have conferences every other year. The last one was in Shanghai and was in 2020. It was an online conference, and the next one will be in Barcelona next year. You can join this association. It's no fee, and you have about 2,000 members and 12 national groups, including one is the Sri Lanka group, but you have the US groups, the US groups, the Brazil groups, Australia, China, Japan, Brazil, and others, Italy. So this will be the conference in Barcelona in June. Hopefully it will be in person, but we don't, in July, it will be in person, but we don't know yet. And this is another association of life cycle civil engineering. This was founded in 2006. We have about 700 members, more than 700 members. Again, you can join this association. Again, you have every other year a conference dedicated to life cycle civil engineering. The next one will be in 2023 in Milano. So with this, I want to thank you very much for giving me the opportunity to present this lecture. I want to thank especially Professor Jahan Flor, who contacted me, he invited me, and we corresponded very much during the last month. Thank you. Thank you also for introducing me, and thank to everybody for giving me this opportunity to present this lecture. Thank you again.
Thank you, Dr. Frangopol, for this very useful presentation, and also for maintaining time. We appreciate your time and support, and we do have time for 3 questions, and I have 3 questions that have been submitted from the audience. The first one is actually something that I'm also extremely interested in. You talked about climate change and the increased uncertainty in the frequency of hazards like floods, cyclones. How do you think this additional uncertainty in the future will affect the modeling of lifetime resilience?
Yeah, these are very good questions, and I can just report that we are looking at climate change is American Society of Civil Engineering has now a committee looking at this and trying to put up a report. There are about three groups. One group that is working on the meteorological part and climate change part. These are most people working in climate changes. They don't have too much relation with structural engineering. The other group, two, is working in predicting, looking at different aspects of climate change and how could be applied to civil engineering, and also how we can modify generally the structural code. So these are committees that are looking at the structures effect of climate change. And my committee, the committee 3 that I am chairing, the committee 2 is chaired by Professor Ellingwood, and we are looking at management decision-making under uncertainty. So it's a difficult, very difficult process. We are looking at all these data that were given to us by the working group 1 and also data that are now with climate change. And we try to do our best, but our prediction could change very much. So we are thinking that all this, the passage of Infrastructure Investment and Job Act that was a month ago, I think this will have in the United States, this will have a monumental impact of economy, public safety, and global competitiveness, and climate change will be one of the parts. By the way, the chair of the Group 1, which is working at the NIST, was named to consult with the White House on this problem. So this is a national problem and will be very important.
My next question is actually something that you just alluded to about the role of government. The question comes as follows: how does the engineering community make the public and the socio-political leaders who are involved in public policy aware of the risks and hazards encountered during the lifetime of an engineering structure?
Yes, I think, American Society of Engineering did an extremely good job. They begin with this report about 20 years ago. They publish this report every 5 years. They have contact with the Congress and they educate people in the Congress, because In our country, the Congress is deciding about allocation. So there are interaction between American Society of Civil Engineers that are publishing these reports. As I mentioned, I show you some grades, C minus, D, B. So in this way, they can communicate and they have representatives. They can communicate with people in the Congress, in the Senate, and take decisions. So I hope that other countries will do the same thing. Having civil engineering associations looking and reporting to the government, or if not reporting, just saying, we have a very difficult situation. We have to help us. This is a situation. These people want to do this and so on. So it's a kind of political thing, but I think we have to initiate this. Every country has to have this type of thing. And we are very proud to have now this 1.2 trillion bills that will help very much our transportation system, our infrastructure system, and so on.
Thank you. The last question is, do you think there needs to be a paradigm shift in the way structures are designed and the materials? What is the future of materials in structural engineering? Keeping in mind with all the hazards that are out there, should there be a paradigm shift in structural design? I myself am not a structural engineer, but I am interested on should civil engineers start looking at, structural design outside the box? Or is it business as usual?
No, I think now, all the designs that we have until now, even in the United States and so on in the world, generally, they don't put the time aspect. They don't have the time aspect into consideration. Now, more and more, the time aspect is an aspect that has to be taken into account. For example, projects that are above a certain amount of dollars, they have to tell what is the total cost, including maintenance, repair, and so on, for the next 50 years or something like this. So is a great move for education now in life cycle engineering. 25 years ago, almost nobody talked about life cycle. People didn't look at maintenance so much. So now, with this deterioration process, even structures that are built in different countries after 5 years begin to deteriorate. But what you ask me is important, and you think that this will also change the structural codes, no? And in general. So things that was, for example, in the building codes, that is an event that have a recurrence period of 100 years. You can see this event happen now every 2 years, whatever. So everything that is in code has to change due to climate change, due to the increasing frequency of these events and so on. So the earthquake in Japan that was in 2011 was a 2,500 years return period. So they prepare now for another earthquake that will be perhaps larger than the earthquake in 2011. So it's a shift now in codes. And as I mentioned, this committee is working groups, especially working group 2, is looking how will be the effect of non-stationarity, all this effect, how will be reflected in new reliability indices. So how will be the new reliability? So it will be a change in all the codes, I suppose.
Thank you so much. Again, on behalf of the BUET Alumni Association and the JRC Memorial Lecture Advisory Committee members, we appreciate your time and effort for delivering the inaugural lecture and, I guess getting us started off in the right direction. Ladies and gentlemen, those of you who were able to join us in this live session, we thank you for your time and efforts. I know some of your students who graduated under your leadership, Dan, are in this session. They joined us and they were very excited that you were talking about a topic that is dear and near to all the hearts of civil engineers around the world. I had the privilege of meeting Dr. Frangopol yesterday. I drove down to Lehigh to thank him personally and also to present a plaque on behalf of the BUET Alumni Association. And I was able to capture this in a short video, which we will try to play right now. It's a great pleasure and honor to present this plaque to Dr. Dan Frangopol on behalf of the BUET Alumni Association as the inaugural speaker for the annual GRC Memorial Lecture. We are so pleased and we are grateful that you made time for this lecture. And I know wherever GRC is, he's a very happy camper today as he watches Dr. Frangopol deliver the first inaugural lecture. Thank you so much. We are very appreciative.
Thank you very much. I'm also very honored to receive this one. Thank you.
Thank you everyone for joining us today. So that was my trip yesterday, and it was a pleasure to meet Dr. Frangopol in person and talk about issues that are near and dear to the heart of GRC and his own contributions to education and research in infrastructure. Next, we are going to end this session. And again, thank you so much for joining us today. This session has been recorded and will be placed. So individuals who were unable to see this can watch this later. Before we go and move to the vote of thanks from the Memorial Lecture Advisory Committee, I do want to thank you from the members of GRC's family. I am actually his niece, but I know there are family members, his daughter, his son, and his wife. They thank you from the bottom of their heart for making time to present this lecture. We are now at the end of the session, and we are going to hear from Dr. Sadiqul Islam Bhuiya, who's a close friend of GRC and also serves as the Secretary General of the BUET Alumni Association. And he's also chairing the GRC Memorial Lecture Advisory Committee. So we are going to hear a vote of thanks from Dr. Sadiqul Islam Bhuiya.
Mr. President, respected speakers of this momentous and historic event, ladies and gentlemen, at this final point of the event, I, on behalf of BUET Alumni Association, would like to express our deep gratitude and appreciation to a number of most valued individuals. First of all, we are grateful to Dr. Dan M. Frangopol, Fazlur Rahman Khan Endowment Chair and Professor of Civil and Environmental Engineering at Lehigh University, USA, for graciously accepting our invitation to be the inaugural speaker of this event. We most sincerely thank him for sharing his profound knowledge and experience on the theme of his lecture. We are grateful to Dr. Kausar Jahan, Professor and Head, Civil and Environmental Engineering Department, Rawan University, USA, and member of the JRC Memorial Lecture Advisory Committee, for aptly introducing our honored speaker, Professor Dan M. Frangopol, to all of us in this event. We are grateful to Professor Satya Prasad Majumdar, Vice Chancellor of BUET and Chief Patron of BUET Alumni Association, for his earnest participation in the event and for delivering a passionate homage to the memory of National Professor Jamilur Raja Chaudhuri. We are thankful to Engineer Moniruddin Ahmed, Acting President of BUET Alumni Association, who has been a strong pillar of support to all our activities during the trying times following the sudden passing away of our beloved President Jamilur Raja Chaudhuri. We are thankful to Architect Qazi M. Arif, Secretary for Communication and Publication, BUET Alumni Association, and a member of JRC Memorial Lecture Advisory Committee, for aptly steering this event. We are thankful to him also for doing all the graphics work that we used in campaigning for this historical event. We are thankful to Dr. M. Mustafa Ali, Professor of Water Resource Engineering Department, BUET, for deftly supporting the technical aspects of this virtual event that enabled interested people from various parts of the world to tune in and watch this event live. We are indebted to Architect Shakur Majid, a nationally recognized writer and photographer, for generously giving his expertise and time to video record some of the speeches for this event. We are thankful to the members of the JRC Memorial Lecture Advisory Committee, comprising Professor Muhammad Delwar Hussain, Head of Civil Engineering Department, BUET, Dr. A.K.M. Masood, Professor of Industrial and Production Engineering Department, BUET, Engineer Mir Mujibur Rahman, Chairman of BUET Alumni Association North America, Dr. Kausar Jahan, Professor and Head of Civil Engineering Department, Civil and Environmental Engineering Department, Rawan University, USA, Engineer Ziaul Islam, Management and Program Analyst, WAPA, California, USA, and Architect Qazi M. Arif, Secretary of Communication and Publication, BUET Alumni Association, for their continued interest in the event and tenacious work for the past several months that made today's assembly a successful one. And finally, and perhaps most importantly, I'd like to thank and express our appreciation to all the participants of the webinar and viewers from various parts of the world for their participation that made this event meaningful and worthy of our efforts. Once again, ladies and gentlemen, I thank you all for your patience and participation. May God bless us all. Thank you.
So we are at the end of our lecture series today, and I want to thank everyone who joined via Facebook Live to listen to Dr. Dan Frangopal. Again, a very hearty thank you to Dr. Dan Frangopal for delivering this very important lecture to all of us. And thank you to all the JRC Memorial Lecture Advisory Committee members. I know many of you have worked hard night and day under very excruciating circumstances. The pandemic is still raging on. You have loved ones who are not well. And I appreciate all the time and effort that has been put in to host this event and to also host it live on Facebook. I know JRC, and most of you who know him well knew that he had tremendous faith in technology and the power of the internet on trying to reach out to the masses, whether it was WhatsApp, Facebook, Viber. He knew it all. And I think we have all made him very happy today, wherever he is. I'm sure, Dan, he loved your talk because this was his meat and bread: infrastructure, resiliency, climate change, and educating the masses. And so thank you, everyone. Stay safe, stay well, and we will be doing this again next year, and we will look forward to many more speakers to come in the future. Thank you, everyone, and stay safe and well.